Okay, once you know the basic area patterns for rectangles, parallelograms, triangles, trapezoids, and so forth, you can go from there to do quite a few other shapes just by dissecting them, so to speak, cutting them up into pieces. So let's go through and find these areas. We'll take the grid as a unit length. So this is 1 unit here, and a square would be 1 unit area. Okay. And so these aren't exactly inches or centimeters or anything, but let's just take that to be 1 unit. Okay. One approach is to cut it into pieces and add them up. Another approach is, like for instance, this one could be thought of as a rectangle minus a triangle. There's a lot of ways you could do this. You could, for instance, chop it into a rectangle plus a trapezoid. You could do 2 rectangles and a triangle. You could do a rectangle minus the triangle. Let's do it that way just because. Okay. So if I continue on out to here, it's 1, 2, 3, 4, 5 by 1, 2, 3. That's 15 minus, this would be 1/2. If that's 1 by 1 and then taken half. And so this is 14.5. Okay. Let's try this one. Let's just try dissecting it into reasonable shapes. Let's bring this down the center and bring this over. I'm trying to make it so that all the horizontal and vertical dimensions are nice whole numbers. And then I can just cut this across, and I can keep on there. I could treat that like a trapezoid or a triangle plus a square. So here's 4, here's 2, here's 3. This is 1, 2, 3, 4, 5, 6 divided by 2 is 3. So it's 3 times 2 is 6 divided by 2. And this one is 2 times 3 is 6 divided by 2. So 3, 6, 9, and 4 and 2, 6. 9 and 6 is 15. Okay. How about this one? Again, if I go across here, I'm going to wind up not knowing exactly the dimension. But if I come down this way, I have 2 by 1, 2, 3, 4, 5. 2 times 5 is 10. Half of that is 5. And here is 2 by 2 is 4. 2 by 3 is 6. Half of that is 3. 5 and 4 is 9, and 3 is 12. Okay, this one, it's pretty clear it would be a square minus the circle that's in the middle. And so the square would be 1, 2, 3, 4, 5, 6. 6 times 6 is 36. And then I'm going to subtract the area of the circle, which is pi times the radius squared. The radius is 2. From here out to there is 2. So pi times 2 squared is 4. Okay, so 36 minus 4 pi. For some purposes, you might just leave it symbolically like that. But if you want to use a calculator, take 4 pi, so 4 times, and here you have to use shift and go down here, and that's pi, equals, that's 4 pi. And let's change the sign, that's minus 4 pi, and then add 36. And it's 23.43. Or however much precision is reasonable. Okay? And what's reasonable depends on your application. Okay. What about this one? If it looks like here's a half circle centered here. Notice the radius here is 3. The radius here is 3. Okay? So pi r squared. But by the way, before we take half a circle, notice here's the other half. Okay, 3, 3. So this is the other. So altogether we have a full circle plus the rectangle. So pi r squared, that's 3 squared is 9 pi, plus the area of the rectangle. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 times 9 is 54. Use the calculator. 54 plus 9 pi, plus 9 times shift. There's the pi equals. 82.27. Okay. Okay, what about this one? This was a circular sector here. And notice from the center out to here, it's 1, 2, 3, 4. So the radius is 4. The full circle would be pi r squared, so it would be 16 pi. Except this is 60 degrees. And if you divide 60 into 360, this is 1/6 of a circle. So divide this by 6, and that'll be the area. If I divide 6 and 16 both by 2, this becomes 3, this becomes 8. So it's 8 pi over 3. Or, if I use a calculator, I'll take 8 pi, 8 times pi divided by 3 equals 8.38. Okay. All right. What about this? Okay. If you look at this and imagine the parts that aren't there, I think what you can see is it would be like a square with circular sectors cut out of it. In fact, the four circles, the four circular parts are each one 1/4 of a circle. So altogether they would add up to a circle whose radius is 2. So let's take the area of the square minus pi r squared. R is 2, so 2 squared is 4 pi. So the square minus 4 pi. So 1, 2, 3, 4 squared is 16 minus 4 pi. Pi r squared. Okay. Okay, 16 minus 4 times pi comes out 3.43. Okay. So this kind of process is pretty straightforward. You just have to be creative sometimes to get chunks that you can rely on for their dimensions. If you're actually doing this in the real world, you have even more freedom because you can just, as long as you have your own measuring tape, you can divide it up any way that makes sense, and you're probably not going to get numbers that come out even. You'll have to use fractions and decimals and things like that to get your answers. Okay. This leaves one more biggie. What about really badly irregular shapes? Now this one I've still gone to vertices that are whole number coordinates here. But say that you're a surveyor and you're trying to find the acreage of somebody's odd-shaped parcel of land. Well, the coordinates of the points, if you plot everything out here, might come out with numbers that have several digits of decimals thrown into it. And so it's going to be a big mess. Trying to dissect this into triangles and things like that could be done if you do your own measurements, but it's, again, a big mess. So what is a good systematic way? It turns out this, I've been saying don't use magic formulas. Well, this is not exactly a magic formula because I'm going to go through and derive it once we're done here. But this is such a simple process to do this kind of a calculation that it's actually worth just memorizing as its own little process. It's not a formula per se, it's a process. And here's the way it works. And by the way, I want to mention, I did not ever find this in a math textbook. I found this method in a surveyor's handbook after I was already out of high school, out of college, already teaching for quite a few years, and I was at a yard sale and I found some surveying equipment and a handbook and all that, which I bought at the yard sale. And then I started looking through the handbook and I found this method for finding areas. And it is so elegant that it's something that it should be in every high school math textbook. But here we go. Start out by listing the coordinates of the vertices. So I'm going to start here. And notice the point here is at 0, 1, 2, 3, 4. So there we are, 0, 4. So x is horizontal, y is vertical, 0, 4. Then I go to 1, 6, 3, 5. Over here is 10, 9, 8. So it's 8, 7, 9, 4, and so forth. All the way around. And importantly, the first is also the last. So if I start at 0, 4, I have to end at 0, 4 because I have to get a complete closed loop so that these duplicate. Okay, that's step 1. Just list them. Step 2, multiply these diagonals. Put the answers over here. 0 times 6 is 0. 1 times 5 is 5. 3 times 7 is 21. 4 times 8 is 32. 9 times 0 is 0. 6 times 3 is 18. 4 times 2 is 8. 2 times 4 is 8. 1 times 4 is 4. Okay? Multiply these diagonals. 4 times 1 is 4. 3 times 6 is 18. 5 times 8 is 40. 9 times 7 is 63. Here. 6 times 4 is 24. 0 times 4 is 0. 2 times 3 is 6. 2 times 1 is 2. 4 times 0 is 0. Okay. Then you add up these two lists. Okay. Over here. 5, 6, 7, 8. 8 is 16. That would be 3 times 8. 4 times 8 is 32. 4 is 36. 3, 4, 5. And 3 is 8, 9. That's 96. Okay. Over here, there's 8 and 4 is 12. And 3 is 15. And 4 is 19. And 6 is 25, 27. 2 and 1 is 3. And 4 is 7. And 6 is 13. This makes it 15. 157. Okay, multiply these, add them, subtract, and divide by 2, and that's the answer. And that's the exact answer. There's no approximations here. This is a completely rigorous method. It always works as long as you start and end at the same point, and if you get all the coordinates of all the vertices. Okay, so let's find the area here. 157. Minus 96 equals 61. Divide by 2. 30.5. Okay. Now, before we derive this, I'd like to show you another very handy thing about this method. It's so systematic that it's very easy to implement on a program or even something like a spreadsheet. So let's pull up a spreadsheet. Okay, you could do this with Excel if you have Microsoft Office. This particular one is LibreOffice. There's OpenOffice. There's a variety of spreadsheets available. If you have a Mac, there's other spreadsheets you could try. All I've done so far is I've just listed 2 columns of numbers. Notice 0, 4 is here. 1, 6, 3, 5, and so forth. I've listed all of these pairs of numbers right here. In a spreadsheet, you can put numbers or other data, or you can put formulas. And a formula is just instructions on how to calculate the value of that cell. To enter a formula, I have to start with an equal sign, and then I say, what is it I want it to do? So I'm going to say this number, whatever it is, times, and I use an asterisk for that. And then I say this number. And so then I say enter. So if I click on this, notice up here it says B2 times C3. Let's look at that. Here's B2. That's the 0. This is B2. And here is C3. So this one is C3. And this one says B2 times C3. And it turns out 0 times 6 is 0. Okay? Now here's the beauty of it. See this little box down in the corner, the little black dot? If I grab that and pull it down, there. And so each one of these, it's in a relative terms, it's going to be this number times this number. So this is B5 and this is C6. And up here it says B5 times C6, and so forth. Okay? Now on this side, I'm going to say equals this number times this number, and enter. 4 times 1 is 4. Take that, pull it down, and there are those products. Just check one. Here's the 63. That's 9 times 7 is 63. 24. 6 times 4 is 24. So forth. Okay, let's take this and add up this column. There's a function here. In fact, notice that this little F symbol here is for various functions. If you click this, it'll list dozens and dozens and dozens of functions you can choose from. But one of the functions says sum, sum, like you want to add up a column. So I say equals sum. Then I have to put parentheses. Notice it's telling me what I have to do. Open the parentheses and then scan over the range of cells that I want to add up. I say enter. And then this one is going to be equals sum, opening parentheses, and scan over this range of cells and say enter. Okay? So down here I want to say the area is equal to, now that equals is not going to be a formula, that equals is just part of the text after I already typed in area. Alright, then here I want to actually put in the formula. Okay, for this one I start by saying equals. I'm going to need to use parentheses because of the order of operations. I have to subtract that minus that, close the parentheses, and then say divided by 2. If I didn't use parentheses, it would just divide the second number by 2, and that's not what we want. Okay, there's your 30.5. That confirms what we did by hand here. And if we change the numbers here, then this was automatically changed. Okay. Okay, here I've done the same kind of a spreadsheet kind of computation as before, except I'm using the spreadsheet that's built into GeoGebra. And what I've done is I have these two columns are lists of points, and notice they're not put in there as whole numbers. I put in more involved numbers just to illustrate the idea. And then over here I listed them. I created a list of points. That put them over here in the geometry view. And then let's see, if I go into geometry view, then I'll use this polygon feature, and I'm able to actually create this polygon. That's the shaded region within those same vertices. Okay. Now over here in the algebra view, it shows poly 1. That's this one right here. And it says 8.49. And that's what I'm displaying here. I'm displaying the value of the area of the polygon as computed by GeoGebra itself. Over here, I'm taking the list of points, and I'm computing the area of the polygon, and notice they agree. Now the interesting thing here is I can take these vertices and move them around, and notice that the area changes, of course, but also the computed area over here changes, and it's constantly in agreement. So what we're doing essentially is what the program is doing. When the program tells you that the area of this polygon is 8.34, you might have wondered somewhere along the line, how did they figure that out? How did the programmer know that that polygon has this area? Well, this explains it. So this is the standard way to find the areas of very irregular polygons if you know the vertices.